Then the last time we stopped at the definition of talk about the spherical completion of a field. And I said that generally, contrary to the Archimedean case, it can happen that we can find some sorry. Then the last time I give the I said that in some for a complete ultrametric field, there is no reason to for a decreasing closed ball to have a non-empty intersection. And if in the case every decreasing, because a definition. We say that K is spherically complete if any decreasing in the sense of the inclusion. So empty intersection. Then, as an example of such such set. I will explain any fields, what I mean by discrete valuation later, just later. Complete ultrametric field. With discrete valuation. This means that the image of this means that the image by the absolute value of the fields is a discrete subgroup of R plus. That's what I mean by discrete valuation. Is spherically complete. As an example, we have QP endued with the p-adic absolute value for sure, because this just to mean the image of the multiplicative group of QP, and we know that it is exactly something like that. Then it is discrete, and we have the other thing, the other fields, the fields of Laurent with the p-adic absolute value, and we know that in such situation we have the same. It is just here for R or the absolute value of T last time just I didn't what is the I talk about the completion of the algebraic closure, but I didn't talk about one of QP. We denote by CP by the completion of here it's p-adic absolute value is equal is isomorphic in some sense to the completion of the algebraic closure of QP. And in that case, we have that in that case, we cannot just just the residue fields is exactly the algebraic closure of FP. And here just, and as an example of a non-spherical complete fields, we have CP. And here we have just something like that. However, the proof is not easy, is not spherically complete. Now give some notation. K is a complete field. Then denote by, as I said before, the image of and we have that is a subgroup of then if is discrete, then we say that for example, then now we will talk about something new. We have our fields. If we consider an extension of a field, then we have the degree, a finite extension, then we have the degree of this finite extension. Now we will explain what is the link between the degree of the extension and the degree of the extension induced to an extension between the residual fields. Then what is the link between the degree of the extension and the degree of the extension of residual fields? And let L be a finite extension. Then we have two, if you have an extension, then we have two new information, the residual fields and the group, the subgroup of R of the image of the absolute value by the image of K star by the absolute value. And we have another value, and we set is equal to then, for example, if we consider the fields, no, I will give some example before talking about the theorem. Sorry, is everyone? Then, now we will give some other example of some extension of the fields that they are not, and how this value that they are not algebraic. Now suppose here that is algebraically closed. Let's see, K and R. Then we will consider the fields. The fields that we introduced before, which is just the completion of the fraction field with respect to the R Gauss norm with centers C. Then we have the following situation. Now we will compute the residue field of each of the group of the image of the multiplicative group by the absolute value. Then we need to distinguish two situations. If R is in this group, this is a particular situation about ultrametric spaces. Even, for example, if we have a complete algebra, a complete algebraic, no, a complete ultrametric field who is algebraically closed, it can happen that for example, as for CP, it's not equal to R plus, and there is some value that they are not in the group of valuation of the absolute value. And then in that situation, we can prove that the residual field of XCR is exactly the fraction fields with coefficient in the residual field of K. And in that situation, these two groups are here. Just this definition is available for any extension, not necessarily algebraic, not necessarily finite. They are equal, which mean that we have is equal to 1. Then if R is not, then in that situation, the residual field is exactly K, the residual field of K. And in that situation, we can also express this field. Not only we have a nice presentation of these fields, we can represent it by convergent Lorentz series. No, not by a series defined. You can say on an analysis, but it's not. It's not the field of series. In that case, it can the negative power can be infinite. The number of infinite power, negative power can be infinite. However, they are convergent, which means each part is well defined. And the residual field, as I said, later we will study differential equation especially in such kind of fields. We know that it is a subgroup of the multiplicative group. Multiplicative group R plus star, and it is generated by and R. Oh, sorry, here it's sorry, here it's to 0. And in that situation, it's equal to 1. No, cannot. It's not a finite extension, cannot say it. Just the degree of transcendence, degree of. Wow. Then, in particular, if K is trivially valued, Then a simple example of here I didn't say, but if we have k trivial evaluate, then in particular, since since the value of the absolute value are only 0 and 1, then it is a discrete subgroup. Then one is a discrete subgroup of R plus it star. Then trivially evaluated fields are spherically complete. This is just another example. Then it is isomorphic to now we will try to understand if this is the assumption is still available, we will not change it. Then if we consider, generally, if we consider we cannot classify directly the non-algebraic extension, but if we consider an extension of and we consider Z an element of omega, we set Hz to be just we know there is two situations. If Z is in K, then it's algebraic over K because it's an element of K. Otherwise, it will be a transcendent element, and K fraction, the fraction on Z will be isomorphic to the fraction fields. In that case, we just consider this field to be the completion of this subfield of omega with respect to the absolute value in omega. And we know that since it is an extension, then this absolute value extend this one. An extension, just I mean that this field embed isometrically on this field, which means that in this absolute value extends this absolute value. If Z is in omega, not in K, we say that Z is a generic point. this height mean the completion with respect to this absolute value. And here is its mean. Tilde here means it's here. It doesn't mean the completion. It just means the residual field. And by the residual field, I mean OK over MK. Then we define another value for such a point. We can, for any transcendental point, we can define the radius of the point. In some sense, how far this point is, how z is far from the point of k. Then we have, for this value, we have several situations. And if the radius of the point is exactly some element z minus c, then we have its z is isomorphic. And if the radius of the point can define it for any point of omega, not only the point that they are not in. And in that situation, if the radius is equal to 0, this just means that z is an element of k. And be careful here. I suppose that k here is algebraically closed. Then if is strictly less than z minus c for all c in k, then we can find a sequence such that c minus cn converge or decrease to chi. And in some sense, this means this just define, we can define by that a sequence of decreasing closed disk. I call this R1. A sequence here just to mean that the element of the disk are in k and not in omega. in particular. Because of that, because it is exactly so, then it's equal to the empty set. However, in omega, then we will recover we'll find the disk that it disappear in K, because this situation, if we have this situation only if our field is not spherically complete. Otherwise, it will be zero or this situation. Then it is exactly here, this closed disk of center C and the radius K. T. And in that case, then it is also the completion, but with a special absolute value that we can define using the Gauss norm, but in a very specific way. And here it's just considering the Gauss norm with center Ci and radius Ri. This is an absolute value. And we can express any absolute value in this field with using this this formula. However, for example, if the decreasing disk are equal to the intersection of the decreasing disk are exactly equal to some disk, then it will coincide with the Gauss norm. Then just under obvious situation, if chi Z is equal to 0, then Z is in K, and here HC is K, is exactly K. Then we can classify our point as follow, and they have a name. The first one, point of type 1, if K C is equal to 0. Type 2, And we will just, as I said before, even if they looks like the same, this kind of point, they looks like the same. It looks like the same, that we distinguish these two cases, and for the type of the point, we will distinguish between these two cases. Type 2, then arc I C is equal to Z minus C, and is in have the same, but we distinguish between these two cases because the residual field and the group of the absolute value are not equal. That's why we distinguish. And the last type, it doesn't exist is if our field is, therefore it's not equal to, it's not equal to 0. Because if we have if it's equal to 0, then probably, since the field is complete, then we will got a sequence that converges to 0, and in that case, it's probably an element of K. And just say something about this kind of extension. In that case, and in that case, we have something strange. Then the residual field is exactly K, and the group of the absolute value, the value of the absolute value, is exactly equal to. And any extension satisfying this, we call it an immediate extension of. Then theorem. Now we can if we have a finite extension, we will give the relation between the degree of the residual field and the degree of the extension. Theorem. Here we don't assume that K is algebraically closed, just an ultrametric fields. And for example, if it can be a fields of this type, for example, we will not assume that. There we have. And generally, we have is always greater or equal than However, in the most interesting field that we will consider, we have the equality. Then in the following cases, just a remark or a lemma. If the residual characteristic of K is equal to P, I'm not talking about the big fields. The big field, even if it is of characteristics 0, the most it will depend on the characteristic of the residue field. Then is a power of P for some n. And be equal to 1. In the case if we have the equality, then it is equal to 1. That's why for example, if the degree of my extension is prime with P, then probably we have the equality. And for example, if my fields, the residue fields is of characteristic 0, then in that case also the equality holds. And it can be extended to other cases. For example, if we consider the extension of an ultrametric, complete ultrametric field with the discrete absolute value, then in that case we have the equality, as we know, for example, for the QP, we have this equality. And the good thing is that also for fields like, and just like in the following situation, is an equality. This is for another reason, but it's good. Discrete. Secondly, we have this kind of fields, for example, using some extension fields. the case the characteristic of K is equal to P and P don't divide the degree of the extension, and in the case of the residual characteristic, it's equal to 0. Now, for example, if we come back to what we said before, if we consider these fields and we consider a finite extension of these fields, then if I am dealing with point of type 2 or 3, then it's okay, we have the equality. However, if we have a point of type 4, in this case, this can happen if my field is not spherically complete, then if the degree of the extension is divided by P, then we don't have equality. But it will not enter us to this situation. And from now on, for the rest of the course of today, I will assume that we have the equality for the rest of the course of today. We will talk about the unramified extension, the totally ramified one, and the moderate ramified extension. That any. Then let L be a Galois extension. Okay. Then since for all sigma in the Galois group, sigma is an isometry, then in particular, sigma stabilizes the maximal ideal of L and stabilize the ring of integer of L. Then we can have naturally an isomorphism of fields such that this is well defined because of this. Just associate the residual. Hence, we obtain natural and from the Galois group to the automorphism. The allotomorphism that I fix K. And we denote by the kernel of this morphism and call it, and this is what we call the ramification group of the extension L over K. Then we say that suppose that we say that L is a finite unramified extension of K if and only if, in one hand, we have and this is important. There is the extension. This extension should be separable. In other words, this just means that the degree is equal to the separable degree of this means the maximum separable extension between sub-extension between sub-extension of L. Then, in this situation, we can prove a limb proposition. We have one-to-one correspondence between then if then, for example, you just give an example if an example of a non-ramified extension, even if we have the same degree, assume that the characteristic of K is equal to 0 and residue fields. Oh, just as we just consider CP in that case. We said here K is equal to CP. And we consider then I consider just the extension L to be the one if we have we call just omega here. We call this field omega. And consider the extension, the following extension. Then and the degree here is exactly equal to P. However, know that the residual fields, this is exactly And we know that this extension is purely inseparable extension. Just mean that because the polynomial xp minus t is just equal to the minimal polynomial of these elements, we can prove that it is irreducible easily. It's exactly because we are in characteristic P. No, this is just an example that even if we have they have the same degree, but why we will consider it such a way? Because in this situation, if, for example, my extension is purely inseparable, then the automorphism are reduced to one of and in that situation, the ramification group is equal to all my group for this example. Just a remark. Now, just a definition, another definition. We say that L is a non-ramified extension if for each subfinite extension of L over K sub-extension L prime of L finite over K L is ramified. If L is unramified, then is a separable extension. If moreover L is Galois extension, Then so is for, and in that case, from one hand, it is an isomorphism. And on the other hand, this is exactly the Galois group. Just a point, if even if L is not unramified, if L is a normal extension, then so is for the extension of the residual fields. Mm-hmm. And in particular, if it is unramified, there is an alternative definition for Galois extension that we can define it as just that the ramification group is equal to 0, is equal to the unit, reduced to the unit. Then definition, another definition. Now we need to define what we mean by unramified ramified extension. In other words, totally ramified extension, not ramified. Ramified, if it is just, it's the opposite of unramified. But what we mean by totally ramified over K. In that case, if the extension is Galoisian, you just need to say that this morphism is the kernel is equal to the ramification group is exactly equal to all of the Galois group, but we can define it even if the extension is not Galoisian. Definition. Then first of all, since we can define the notion of maximal unramified extension of on fields, and we say that is totally unramified the maximal unramified of K in L is K. This just means that we cannot find M strictly such that M is Now we will talk about a specific one, which is interesting, even if it's an unramified extension, but it behaves like an unramified extension. And we can find its Galois group easily for then if and here just to say in that case if then in that case, if it is totally ramified, then we have exactly that. L is totally ramified. And let L be a totally ramified extension of L of K. We say that that is tamely ramified if and only if we have the following. Then the first one is that this is separable. Second one, the characteristic if the residual characteristic of K is equal to P, then P don't divide as an example. This means that if the residual characteristic is equal to 0, then any ramified extension is tamely ramified. Because if the residual characteristic is equal to 0, then any extension is separable and everything is okay. Example. If we consider, for example, m is an integer, just to prime number, any integer is okay. Just to simplify things, but it's okay for any integer. And the characteristic of K is equal to 0. And K equal to 0. just consider it's equal to 0 because it will be the residual fields. And we consider the fields. And any, and for example, if we consider the just consider this is exactly then in that situation, then residual field in both cases are isomorphic, and they are equal to K, which is of characteristic 0. And we have is exactly equal to P. And in this situation, this group, the Galois group of this extension is a cyclic group. Just to have the notion of cyclic group, otherwise we will just have the and it is C over PZ, which is isomorphic to generally if it is an M, and then it is the same situation. And more generally, if we have a terminally ramified extension, then we can come back to an extension of this kind. Maybe I just need to and we may stop here. Then just the idea why we are interested to the why I introduce in the case of an ramified extension of a term or a terminally ramified extension, if we have a differential fields, if we have the idea is the following: if we have then K and we have D a bounded derivation, in some sense it just means that it is continuous. Then if we have a terminally ramified extension or unramified extension, or unramified, then this derivative extends uniquely to L and the good part is that spectral norm as an operator will not change. and we just the spectral norm is equal to. Then we finish here, and see you the next week.